Okay, thank you very much, everyone, and very happy to be here today. I've been saying it to everyone all morning, but it's a real thrill to be here. So my name's Gregory. I'm a postdoc at the University of Arizona, and I'm working with Professor Alejandro Salado, where we are developing a digital engineering factory there, and the goal is really to support the engineering curriculum and to support engineering students. So I'll give you an overview today. So I want to start with something we can all agree on, is this idea that silos, when we look at them like this, generally bad, right? We don't want the software to not be talking to the electronics team or the aerodynamics team. So I think this is agreed upon, and we've all seen these kind of diagrams before. But if it's not good enough in industry, then why do we tend to take this approach when we're discussing engineering curricula? So what we have at the University of Arizona in our Systems and Industrial Engineering department is something like this, where we have our systems courses and our software courses are treated like silos. The students work within each of those courses in tools that don't talk to each other. They generate work products that then don't influence other work products down the line. So what happens is that students don't tend to get this experience of working in a digital engineering environment, and they're not able to work on projects, work on things like requirements, and then see the effects of some of those decisions downstream. What this also means is that the students tend to have a limited scope for collaboration. If we think about certain students might be working in particular courses that in teams that don't align well with other courses. So what we're interested in doing is trying to recreate a digital engineering ecosystem and bring some of that technology to the University of Arizona. So one thing we did early on when we started this project in earnest about a year ago is we identified 11 use cases within our department where we thought a digital engineering approach might be able to help the student experience. So 6 of these were software use cases, and 5 were to do with systems engineering. And of those 11 use cases, 7 of them represented existing workflows in courses that are currently being taught. So it was taking things that students might be interested in doing within a particular course and bringing that into a digital environment. But there are another 4 where we thought, well, if we're developing a digital engineering factory for students, we might be able to introduce new capabilities. So we're talking about capabilities inspired by some of the things that OpenMBE are doing and some of the things that OpenCESA are doing. So what that meant is, while some of the use cases that we were interested in could be addressed by things like OpenMBE, and some of the CI/CD stuff could be addressed by pipelines available in GitLab, as we brought that a bit more up to date. There were others that we wanted to address through the use of ontology, and in particular, we were interested in using OML to support some of the data within those courses, and OML Rosetta. So we came up with this proposal for 4 of those workflows, where we envisaged that students would be working in different engineering tools, and data would be integrated into a data repository. So we did an analysis of some of the tools that were available that we could do that, and we went with the Violet tool, which is being developed by a San Francisco-based company called Violet Labs. And what they're able to do is integrate data from tools like Jira and Jama and a few others, and capture that in a core central data repository. So one of the other key capabilities of the Violet tool is that they can take that integrated data and generate OML. So that's where work on the University of Arizona side came in, where we were interested in supporting that integrated data set with a collection of OML-based ontologies. So we produced this initial software architecture. So this is the preliminary digital engineering factory. And what you see here is we have a bunch of tools that were chosen to support the courses that we were interested in. So there was 11 use cases that support systems and software students. And as I say, 7 of those use cases involved using things like OpenMBE and GitLab. So what we wanted to do was get those up and running within our digital engineering factory. But some of them involved OML. So what we wanted to do then was connect. We're working on these connections between discipline-specific tools to the Violet tool so that we can generate representative OML and really go to work on it. And one of the use cases that I'm talking about is to support instructors with things like grading. If we have students working in teams and they want to develop a collaborative project, what we can now do is we can consider integrating all of the data produced by the students in that team across different tools, pulling it together in Violet, generating the OML representation, and then we can use things like validation rules and queries to help the instructor in the grading process. So that's something that we're looking into. So in order to support the OML data that's being generated, of course, we need a suitable selection of ontologies to support that data. And we have a preliminary set of ontologies that we're calling the University of Arizona ontology stack. Now, what we have here, the set of domain ontologies that we've presented here is an ambitious goal. And while we do have instances of each of these ontologies at the moment, I have to say some are more developed than others, and we have we've done some preliminary work on things like the system architecture ontology, the requirements ontology. But what we want to do as we move forward is to really mature these ontologies to fully support requirements data and systems architecture data in a way that's in line with relevant standards. And as you can see, we're building on more fundamental ontologies, but at the moment we're using the basic formal ontology, or a version of it, a simplified version of it at our foundation layer, and the Common Core as well. So, but there's much more work to be done on this, and the ontology stack continues to be a work in progress. Final slide here. So I didn't have time to get into detail on any one kind of use case or any one case study, but we have put out a few conference papers that discuss some of those use cases in a bit more detail. So if we go, I'll just skip back just quickly to the architecture diagram here. So one of the examples is that we take a typical student project and import things like system requirements from JAMA and project management information from JIRA, things like tasks and the students that they've been assigned to, as well as some work products like architecture developments and analyses. And then we can use our project management ontology to show which students contributed which work products. So that particular example was done on a Mars rover. But just skipping ahead again, we have other examples of how we might use Bayesian networks to support verification planning. And we've got a couple that are in the pipeline there that aren't currently released. And we've just recently at SciTech a couple of weeks ago presented a closed loop orbital analysis example where we pass inputs into the Sidaro orbital simulation tool, generate eclipse times for a low Earth orbit spacecraft that we can then use to verify a particular requirement. And then once we have that comprehensive data set, we can use our ontology stack to then check, have we verified the requirements that we're interested in? So if you're interested in looking at any of these in more detail, that's there. But that's all for me for now. Thank you very much.